The question that I have is, could you explain what a dot product between two vectors is? Let me give you a little background on why do we even bother with the idea of what is called the dot product. Let's say we have two vectors, vector A and vector B, both of which are acting at this point right here. Both of these vectors lie on this two-dimensional plane, xy plane. So the angle between the two vectors is theta. Let's consider this question. Given A in its component form and B in its component form, find the projection of A onto B. From the picture here, we see that the projection of A onto B would be simply OC, the length of OC, right? By considering this right triangle, OAC, we see that OC is simply OA cosine theta, but OA is the length of the vector A, which is square root of AX squared plus AY squared, right? Since these components are given, we can go ahead and calculate a value for A, but we need a value for theta to complete the solution here, right? But we can find that angle like this. Referring to this picture right here, we have the components of A, and therefore we can go ahead and find this angle alpha, right, for vector A, which is the angle that vector A makes with the positive x-axis. So alpha will be equal to tan inverse of this distance divided by this distance, which is AY divided by AX, right? We can do the same for vector B. So we have the components for vector B, and therefore gamma will be equal to tan inverse of BY over BX. And it's clear from the picture, alpha minus gamma is theta. So that's what we need. Now going back to the original question, which is to find the projection of A onto vector B, we have everything we need. We have little a, which is the magnitude of vector A. We have the angle theta, and therefore we can calculate the projection by this equation, right? But what if these two vectors, vector A and vector B, are actually three-dimensional? In other words, they don't both lie on the same two-dimensional plane. You can see then the calculations are going to become pretty tricky, right? So this is where this concept of dot product, which I'm sure you learned in your math course, becomes very useful. While the dot product is really useful for three-dimensional problems, there's nothing that says you cannot apply that to two-dimensional problems. In other words, I could solve this problem a little easier using the method of dot products than this method. So let's give the formal definition of the dot product. The dot product between two vectors, vector A and vector B, like shown in this picture, is given by this equation. A dot B equals A times B times cosine theta. We are using the same conventions for the notations here, like before. Little a is the magnitude of vector A, little b is the magnitude of vector B, and theta, of course, here is the angle between the two vectors, vector A and vector B. And here, of course, we are assuming that both vectors, vector A and vector B, are acting at the same point, point O. But in general, of course, they don't have to. And if they don't, for the purpose of understanding what the dot product is, slide one of those vectors over and bring it and attach it to the other vector, like in this picture. The angle theta here is the smallest of the two angles between the two vectors. For example, if I have two vectors like this, and if this angle is 120 degrees and this is 240 degrees, the angle to be used in the dot product here is 120 degrees, not 240 degrees. Two important notes before we move on. First, note the way a dot product is written. For the dot product between A and B, we write it like this. We write it with a dot in between the two vectors. The second important note here is that while A and B are vectors, right, but A dot B is a scalar. We basically get a number out of the two vectors. Let me also add one more note here. It's easily seen that A dot B and B dot A are equal to each other. A dot B is A times B times cosine theta. B dot A would be B times A times cosine theta. You can see both of these are equal to each other, and therefore you can switch the ordering of these two vectors. You get the same results. What do we get if we apply the dot product between two unit vectors along the x, y, z Cartesian coordinate axes? Well, this is what we get. I dot I would be equal to 1 times cosine theta, right? Just by definition, right? The angle between I and I is 0, right? Now recall that cosine 0 is 1 and cosine 90 is 0, right? So we get 1 for I dot I, and similarly we get 1 for j dot j and k dot k. On the other hand, if we try to find the dot product between two different unit vectors like I dot j, you end up having a 0 value for that because the angle between the two is 90 degrees, right? And similarly, I dot k is 0, j dot k is 0. These results allow us to find A dot B in terms of their components. So using their component form, A dot B can be written like this. And note that there's a dot here. Now we expand this and simplify using these results. When you expand it, you want to put the dot between the two vectors which are being multiplied with each other. For example, when I multiply this first term with this first term, we get ax times bx times I dot I. So you want to put the dot between the unit vectors I and I. So you end up having 9 components as expansion. Now you're going to simplify it using this result. So here we already established that I dot I is 1, I dot j is 0, I dot k is 0, and so on, right? So there are only 3 non-zero components in this expression, which are these. So we established this important relationship, the dot product between two vectors expressed in terms of their component. A dot b equals ax times bx plus ay times by plus az times bz. As a special case, we note that when a and b are equal to each other, this dot product becomes equal to a dot a, and on the right side, we simply have ax squared plus ay squared plus az squared, which we know is the square of the length of the vector a, right? And therefore, a dot a is simply length of a squared. Let's say two vectors, vector a and vector b, are given in their component forms, and we are interested in finding the angle between the two vectors. Remember, this is what we did in 2D, right? This is not too bad, right? But it is very difficult to do this in 3D. However, the task is simplified a lot if we use the dot product between the two. We just established in the previous slide that the dot product between the two vectors in their component form is this, and by definition it's equal to this, and therefore cosine theta is equal to a dot b over a times b. So you can see by this approach, finding the angle between two vectors is fairly straightforward.